Everyone, welcome to The Explainer. Today, we're taking a truly fascinating journey from the visible, everyday matter you can actually touch and feel, right down into the invisible particles that are secretly controlling our world. We're going to be breaking down the fundamental rules of reality together, specifically looking at the states of matter and exactly how they change.
Now, I want you to think about this for a second. Why does an ice cube leave a puddle of water when it melts, but a block of dry ice just vanishes into thin air? It's kind of crazy when you stop and think about it, right? It's a bit of a paradox. Well, the answer to this everyday mystery actually lies in a hidden, microscopic dance happening all around us, inside literally every single object we interact with. Okay, let's dive into this roadmap. 1. The kinetic particle theory. 2. Phase changes and temperature. 3. Understanding the gas laws. And finally, 4. The magic of diffusion. All right, section 1. The kinetic particle theory. To understand matter, we really have to understand the invisible engine that's driving it. And that brings us to the kinetic particle theory itself. You can kind of think of this as the ultimate answer key to the universe's behavior. It simply states that all matter is composed of tiny particles in a continuous, endless state of random motion. And here is the kicker. Their average kinetic energy is directly proportional to temperature. This one simple rule completely determines whether a substance is a solid with tightly packed, vibrating particles, a loose, flowing liquid, or a bouncing, hyperactive gas. Basically, the whole shebang is all about how much energy those particles have. Moving right along to section 2, phase changes and temperature. Let's see what happens when we literally turn up the heat. Before we get into the pure mechanics of it, I want to pose a little mystery here to challenge how you intuitively think about heat. So if you put a pot of water on the stove and crank up the burner, the water gets hotter, right? Obviously. But once it actually starts boiling, why does the temperature of that boiling water just completely stop rising, even when you keep adding more and more heat from the raging fire below it? Where is all that extra energy actually going? To solve that, we need to walk through what chemists call a heating curve. Imagine starting with a regular old block of ice at step 1, a solid. As we add heat, the particles start vibrating faster and faster until we reach step 2, which is melting. The solid structure collapses into step 3, a liquid. If we keep heating, we hit step 4, boiling, until finally, at step 5, we have a highly energetic gas, steam. It's a pretty straightforward journey from a rigid solid all the way up to a hyperactive gas. So, here is the absolute crucial point. The temperature actually stays perfectly constant during those phase changes. To answer our mystery about the boiling water, the heat energy you're adding from that stove is no longer raising the water's temperature. Instead, that energy is super busy doing the heavy lifting of breaking the intermolecular attractions. Basically, it's fighting the invisible magnetic-like pull between the particles so they can break free and escape as a gas. Kinetic energy, and therefore temperature, only ever increases between these phase changes, never during them. Now, while we're talking about turning into a gas, we absolutely need to clear up a super common mix-up. Evaporation and boiling, they are not the same thing at all. Evaporation is this quiet, surface-level phenomenon that happens at pretty much any temperature below boiling, and it actually causes cooling. Just think of how sweat cools you down on a hot day. Boiling, on the other hand, is a violent, entire liquid phenomenon that only ever happens at a specific boiling point and requires a constant source of external energy. Zero cooling effect there for sure. Which actually brings us right back to our opening paradox about the dry ice. This vanishing act is a process called sublimation. Substances like dry ice or, those solid air fresheners you hang in your car, they grab enough internal energy to just completely bypass the liquid phase altogether, jumping straight from a solid into a gas. The reverse of this is called deposition, where a gas skips the liquid phase and instantly turns right into a solid. That's exactly what's happening when frost forms on your window on a freezing winter morning. All right, let's jump to section 3, understanding the gas laws. Time to look at the strict mathematical rules that govern this chaotic matter. First up on the docket is Boyle's law. An Irish chemist named Robert Boyle discovered that if you keep the temperature constant, the volume of a gas is inversely proportional to its pressure. In everyday terms, if you squeeze a gas, its volume shrinks. Why? Well, because you are literally forcing those constantly moving particles into a much tighter space, which makes them collide way more frequently with the walls of whatever container they're in. And this brilliantly illustrates exactly what I mean. If you look at this U-shaped tube, by adding mercury to the open end, we are doubling the pressure on the trapped gas over in the closed end. And look what happens. That trapped gas is forced into exactly half of its original volume. It's just a perfect, real-world, physical demonstration of Boyle's law in action.
Next up, we've got Charles's law, named after the French scientist Jacques Charles. He figured out that if you keep the pressure constant, the volume of a gas varies directly with its absolute temperature. Meaning, hotter, faster-moving particles are going to hit the walls harder and naturally demand a lot more space to maintain that exact same pressure. You can actually see Charles's law in motion right here. When we add a heat source to the cylinder on the right, the temperature of the gas naturally increases. This immediately pumps up the particles' average kinetic energy. They start flying around so much faster, striking the piston harder and way more often, which physically forces the piston upward, increasing the overall volume. The pressure stays exactly the same, but the space expands.
And rounding out the trio, we have Avogadro's law. Avogadro figured out that gas pressure depends almost entirely on the sheer number of particle collisions. So if you have equal volumes of two completely different gases at the exact same temperature and pressure, they absolutely must contain the exact same number of molecules. It's pretty simple when you think about it. If you pump more particles into a space, they just require a larger volume to keep the pressure from spiking.
Finally, Section 4, the magic of diffusion. Let's look at how these hyperactive gas particles actually travel and mix.
So, we call this spontaneous spreading process diffusion. It's the movement of particles from an area of really high concentration to an area of low concentration. Think of cracking open a fresh bottle of perfume in the corner of a room. Eventually, those scent particles bounce around and travel all the way across the room to your nose. But what actually controls how fast that happens? Well, lighter molecules travel a lot faster than heavier ones, and higher temperatures give those particles way more kinetic energy, making them mix even faster. Now, what's really interesting about this slide is how we can visually measure this happening. In this glass tube, on one side, we introduce ammonia gas, and on the other, hydrogen chloride gas. Right where they meet, they react and form a visible white smoke. In the exact same amount of time, the lighter ammonia gas travels 59.5 centimeters, while the much heavier hydrogen chloride only makes it 40.5 centimeters. It is a literal race between molecules, and the lighter one wins every single time.
But let's raise the stakes for a second here. This isn't just about perfume or watching gas in glass lab tubes. How do life-saving medicines actually know where to go in the human body once you swallow them? It turns out, this seemingly abstract chemistry concept of diffusion is literally saving lives inside our bodies every single day.
The speed and effectiveness of medicine is entirely dependent on diffusion. When you take a pill, the rate at which that drug diffuses from your stomach into your bloodstream completely dictates how fast you're going to feel relief. For example, lipid-soluble drugs are specifically engineered to diffuse rapidly right through your cell membranes. The faster the diffusion rate, the faster and far more effective the medical response is going to be. It is just pure kinetic particle theory in action, doing the work to heal your body. Which brings me to one final, honestly pretty incredible thought. If simply altering things like temperature, pressure, and concentration can bend the rules of matter to literally save lives, what other microscopic, invisible chemical dances do you think are secretly shaping the world around you right this very second? It's pretty wild to think about. Thank you so much for hanging out with me on this explainer. Keep questioning, keep observing, and I will catch you next time as we continue